Good evening to everyone in Japan. Good morning to everyone in Switzerland or Europe. And possibly good afternoon to someone elsewhere. Welcome to the EPFL Virtual Space Tour in Tokyo. My name is Kyoko Suzuki. I am the head of the Science and Technology Office Tokyo at the Embassy of Switzerland in Japan. I'm very pleased to be your moderator today. The EPFL virtual space tour, centers around two science communication projects. One is the Virtual Reality Universe Project. It is abbreviated VRUP. VRUP is a project that takes you on a tour through the universe using the most detailed map of the universe. It gives you a fully immersive experience using virtual reality technology and takes you through the beginning of the space or our universe and throughout the evolution. It's a very informative and at the same time very amazing project. And we have demos here in Tokyo. If you have the chance, we are still here tomorrow. So please come and experience it at Base Q at Tokyo Midtown Hibiya. If you're in Switzerland, there are very nice videos that you can watch of the VRUP, which is the website of the Laboratory of Astrophysics, where the VRUP project is hosted at EPFL. EPFL is the Swiss Federal Institute of Technology in Lausanne, and we are here with EPFL Space Center. The second project that is the core of the EPFL Virtual Space Tour this time is the Tranquility Base. The Tranquility Base is a virtual escape game. It is based on a physical escape game that was developed by the Student Association at EPFL called Space at Your Service. The physical escape game called Switzerland, We've Had a Problem, uses two tents and has teams in each tent to work together and save the space mission on the lunar base. With the pandemic situation, it was difficult to play this game in a physical way. So the Student Association Space at Your Service, together with the Science and Technology Office Tokyo, developed the virtual version, which is now called Tranquility Base. Tranquility Base is also offered at Base Q. Please come and experience it. If you are not, unfortunately, in Tokyo, or if all the slots are reserved, please find Tranquility Base on your app stores, Google Play or App Store. Thank you. We have a very exciting program. The first session will be about Tranquility Base. So you will hear from Mr. Alexander Dumontolu, the new president of Space at Your Service at EPFL. And then we will hear from the second part, the developers of Spacebok. Spacebok, is a planetary explorer, and it can go and research places where people cannot go. You will hear more about it from Dr. Hendrik Kolvenbach. So I would like to move on. However, I need to give you a few house rules. We will have questions and answers, Q&A, at the end of the session. So if you have any questions from the speakers, please ask them through the chat box, and we will pick them up at the venue and ask for you. For the people at the venue, please raise your hands if you have any questions. We look forward to many. So without further ado, I would like to welcome Mr. Alexander Dumontolu, new president of Space at Your Service. Alexander?
Thank you so much, Kyoko. One second, I'm sorry. Great. Thank you, Kyoko. So, good morning, everybody in Switzerland. Good evening, everybody in Tokyo. I am so proud and honored to take part to such event, the EPFL Virtual Space Tour, because it also means for my association and I the launch of a project we have been working on for almost a year now, called Tranquility Base. So my name is Alexandre de Monlo, and as Kyoko said, I am president this year of EPFL Association Space at Your Service. And today I will present you this game. But before that, let me quickly explain what is Space at Your Service. So we are an association recognized by EPFL. We are specialized in promotion of space sciences in multiple ways to the student community and the general public. We work in collaboration with a lot of different space entities, um, such as EPFL Space Center, Space Innovation Laboratories, or government institutions. And I'm gonna give you a little overview of what we do at Space at Your Service. So we are known on the campus for doing what we call astronomy on tap that you can see on the left pictures. These are informal conferences, and the concept is the following: is that a professional person from the space field go on stage and talk about what he does in front of public, but everything takes place in a bar, and everybody has a beer, and after there is a long discussion between the speaker and the public. Some of you have recognized him, but on the top left, this is Claude Nicollier, former Swiss astronaut. He went to multiple of our events, and he will come back in the future. We also go in schools and give workshops to a very young audience. You can see that in the top right picture. We call it Vivalis mission. We prepare students for a little analog mission for about 6 months. And last but not least, Tranquility Base, which has been last year the biggest project for our association. First of all, I think it is important to say this, but this project is multidisciplinary, which means that people from very different worlds were connected thanks to this project. We can count on laboratories, space-related entities, government institution, and a video game studio. And at Space at Your Service, we were coordinated all this work in the aim to create Tranquility Base. Let's move on to what is Tranquility Base. Well, it is an augmented reality multiplayer smartphone escape game on the theme of space. It sounds pretty specific, but the concept is pretty simple. You can see on the left picture someone holding a tablet and actually playing the game. So the game takes place in two different rooms, one on the learner base that you can see on the top right picture, and the other one on the mission control center that you can see on the bottom right picture. These are views taken from a smartphone. So it is a two-player game. Each person has a tablet or a smartphone, and using the tracking system of your smartphone, you scan the ground with your phone, and after a virtual world appear to you, and this is what you can see through the screen of the person playing right now. The scenario is the following. The lunar earthquake has hardly damaged the lunar base, the oxygen is running down, and you have 20 minutes with a teammate to find a solution and save the mission. So this is a collaborative game, which means that you will have, yes, to collaborate with your teammate, find solution together, even if you are in separated rooms in the aim to save the mission. Now I'm going to explain to you why we did this game, but first of all, why it is so unique. Tranquility Base is a science communication tool never seen before in the world for three reasons. First of all, because, as I explained, it is an augmented reality multiplayer smartphone escape game. Also because, and I will come back to that later, because it contains current Swiss space research projects, and also its scenario is based on real science. For example, when you will watch the introduction cinematic of the game, you will see that the lunar base is placed at the center, at the equator of the moon, and this is for real reason. The purpose of Tranquility Base is the following. We want to show through research projects that are virtual present in the game what a lunar base in 2050 might look like. We also want to promote Swiss contribution to the space field and show that Switzerland is indeed a very strong space nation, and of course give people knowledges about space. So I'm going to show you a quick video that's taken from a smartphone that shows what you will see when you will play the game. So this is the lunar base. Let's see here. I will only reveal a part, not what is on the other side, because when you will play the game, you will discover by yourself everything. And this is the Mission Control Center. So yeah, this is what I mean when I say augmented reality is that a virtual world that is present at 360 degrees around you. All right, now let's move on to research projects that are virtually present in the game. I'm going to start by, to make the long story short, so we reached to laboratories and we asked them if we could put a virtual version of the device they are working on into our game and giving them an application. So the first project is a modular origami robot called Mori from the Reconfigurable Robotic Lab at EPFL. And what they develop, they're developing robots that have triangular shape that can fit together in the end to create complex structures. And the application we gave to Mori is that they are the shell. Mori are actually the shell of the lunar base. You can see on the top right picture the shell of the lunar base and those triangular shapes. And on the bottom right picture, a virtual version of Mori is in also present like that in the game. The other projects present in the game is Amisru from Thermomechanical Metrology Laboratory. What they develop at EPFL and what Amisru is doing is that they extract the rock, the regolith, which is a rock present at the surface of the moon. And with this rock, they can extract the oxygen. And the application we gave to Amisru is, of course, that Amisru is the oxygen supply of the lunar base. And last but not least, Space Brock from the Robotic System Lab at TTH Zurich. It is a crazy robot that is made for space exploration. We have the chance to have Hendrik Kovelback from who is a supervisor of this project, and he will tell you much more about it right after me. And the application we gave to Spacebok. So of course, Spacebok is the explorative robot of the lunar base. So I know that some of you haven't played the game yet, but I will reveal some hidden elements because this is also another important way to communicate space sciences. So you can see, for example, on the left side, good luck peanuts that are present at every NASA's launch. On the middle picture, you can recognize probably a little Swiss cube. Swiss cube was developed back in 2009 at TPFL by, I think it was around 250 students, and was launched into space in 2009. And believe it or not, but you can see on the right side lightsaber, because back in the 90s, an astronaut brought lightsaber from a Star Wars movie into space. There are much more hidden elements, so I can't wait to let you play the game, refine these hidden elements, and find the new ones. There's lots. Now, the future of this game. So the game is made to evolve. We want to have more puzzles in the game. Right now, there are 3 puzzles. And we also, of course, want to have more research projects in it. We want this game to getting bigger and to travel in the future around the world at many events. First of all, we will be at Dubai World Expo in October 2021. So the game is available in App Store and Play Store. So and also you will experience how to base queue the game. So I can't wait to let you play the game. But also you can play this game at home. So please download it after the experience at BaseQ. If you want to know more about Tranquility Base, don't hesitate to go to our websites. There's everything I talked to you about, and also some more informations. And if you have any questions, I would be more than happy to answer them. So please don't hesitate to contact me. And last but not least, I would like to thank all our sponsors. Without them, it wouldn't be possible, of course. It started as an idea back a year ago. And now it's a real product. And we are so happy about it. And we can't wait to see what are the next step and where we will go in the future. Thank you so much.
Thank you very much, Alexander. And now, as Alexander has mentioned, and as I have also mentioned, we will have the primary researcher for the Spacewalk project of the four-legged robot for planetary exploration. Dr. Hendrik Kolvenbach of the Robotic System Laboratory of ETH Zurich. Hendrik?
Yeah, thank you very much for this kind introduction. I try to share the screen. Can you confirm that it's visible?
Here, thank you.
Great. Yeah, thank you very much for the opportunity to speak, and also welcome from my side. It's great that you organize this event and that you have the robot also there visible at the exhibition. I'm very happy to talk about the project Spacewalk and also other four-legged robots that we have developed here at ETH Zurich for future planetary exploration. So to start right away, why do we think that this is a nice contribution for the future? Is that there's lots of opportunities for legged systems in space. So if you see these pictures here from Mars on top and the moon and the row below, we see there's a lot of very challenging environments that we want to explore with our systems. So one of the most notable ones is, of course, that we have a change in gravity. So it's only 1/3 on Mars and 1/6 on the moon. And this is something that the LEG system has the potential to exploit. I will come to that very soon. If you look at the topography, we see that we have a lot of these craters. And especially if you go inside a crater or outside of a crater, you have to overcome this very steep and challenging terrain, which is always an issue with wheeled systems. So we believe that LEG systems have quite an advantage in this type of terrain. You also have to change, depending on the terrain, maybe your locomotion gait. So it might look different on a slope versus like a flat area. Now, if you look closer to the lunar topography, we have these very interesting lunar pits, and they might be something where we see future human settlements. But of course, before you send humans in such a pit, you want to explore this. And you can see on the picture, there's quite challenging terrain, and it's not so clear if you can actually overcome this with wheeled systems. And this is a nice opportunity for future LEG systems. Additionally, let's say we have an interesting area on the moon that we want to explore. Traditionally, we mount a robotic arm on the wheeled system to perform this investigation. But with a LEG system, you have the opportunity to also use your limbs in order to explore and probe the environment. So far, however, we have mostly seen wheeled systems, famously, of course, the NASA Mars Exploration Rover. Here's an example from the European Space Agency, and also other nations have sent their rovers to space. Now, talking about LEG systems, there have been already quite some prototypes, already since a few decades, actually. You can see those on the left-hand side, and they've been around really for quite some time now. But since the last decade, we see a rise in these other type of LEG robots. So if you have seen these things maybe on YouTube, they are always some nice advertising, for example, from Boston Dynamics or maybe even our lab, that give rise to this new type of machine. In the following, I want to go a little bit more into detail of the differences. So if you look at the traditional space leg robot prototypes that we've seen so far, we see that those are mostly multi-leg systems. So those have 6 legs or 8 legs, and they can make use of a locomotion type, which is called static locomotion, which means that always 3 legs are in ground contact. That makes them very stable and safe to locomote. On the downside, it's very mechanically complex. So you have a lot of motors, so you take away also a lot of mass to make the systems move. The velocity usually is also limited due to the number of legs that you will have here. And the whole motion is not as dynamic as it could be. So if you look at the new type of leg systems, those make use of what is called dynamic locomotion. So this means that they can also have less than 3 legs in ground contact, but that makes the control problem much harder because they encounter phases during which the system is not really stable and they have to actively control these phases. That, however, allows them to go at higher velocities, also makes things more efficient. And of course, these systems are also capable of performing static locomotion in case you want to have like a very safe type of locomotion. So to go a bit more into dynamic locomotion, we see some examples on this slide of different gait patterns you can make use of. So on the top left, this is some sort of trotting gait. This is very common in animals. If you have a cat, a dog, or a horse, you've most likely seen this type of gait. Then there are other gaits like a dynamic lateral walk here on the bottom left, and even more dynamic gaits on the right-hand side. So like a running trot or a prong. The difference here is that we have phases in the gait cycle during which the robot actually takes off the ground, so it does not have any contact for a very short time. So we can make this distinguishment. So, but why is this something interesting? Because if you go to another type of environment that has lower gravity, let's say, for example, the moon, you will start to see locomotion patterns like this. So here, this is an astronaut moving on the moon, and this is something very common that we've seen. They perform this type of jumping or hopping gait. And if you ever try this in the gym, you will be exhausted very quickly. But somehow, because of the lower gravity, those gaits start to become increasingly efficient. And this is then the reason why we have developed Spacebook here at ETH. Originally, it was a 1-year student project that has developed this type of locomotion platform, which was optimized for low gravity locomotion. So the robot is capable to perform all sorts of dynamic gaits. There was a focus on energy efficient system design, and we use this platform to perform experiments for planetary exploration. The system itself is not space graded. It's still a research prototype, but it's a nice base to explore all sorts of locomotion related tasks for the future. I just want to briefly go a little bit more into the design of the system. Here we see the leg of the robot, and those of you who are physically present can also have a more detailed look on the robot itself. So the interesting part is here that we have the 2 motors mounted at the hip joint of the robot. We can look inside a bit. We see here a high torque motor. This is by the high gap radius, and then a very transparent planetary gearbox. And the 2 things together then basically actuate the parallel mechanism of the link. And because they can work together, this allows the system to perform really powerful jumps. And to demonstrate that quickly, here you can see that in simulation. So this is the same robot, but if we change the gravitational acceleration, you can do very impressive things if you go down with the gravity. So this is nice because it was simulation, but then you want to prove also in the real world. And we performed those experiments at the European Space Agency here, where we have the robot mounted on an inclined rail to offload gravity, to basically simulate lunar gravity. Very quickly, we realized that you have to have means on board to also stabilize the robot during this extended flight phase during which the robot is jumping. So here we added this reaction wheel to the robot to give it this stability. So it has the feet on the ground when you come back back on the floor, basically. These experiments also show that this is a very efficient way of locomoting. We also integrated springs to even increase the efficiency a bit more. And then here we were still restricted to this very linear motion. Then we performed experiments on a flat floor. So this is an area on which the robot can basically move freely, but just on a plane. You will see how this works. It's mounted on those air bearings, and then it can move on this frictionless surface. You can see here how the robot is moving, and the reaction wheel here in the center of the robot is basically taking care of the attitude control. This is something that is also very common if you build satellites. Of course, you can also have some fun with this. So here we have some students playing Pong with the system, and you can see that it works rather smoothly. But this is not really what you want. What you want is something even more agile. If you look at nature, this is very inspiring. You see cats doing motions like this. And this is also something that we want to have on our system, something like this. So in the following, I want to explain a bit like how this can be realized. So there's a new type of control that has been getting more and more traction in recent years, and this is reinforcement learning. So here we have a neural network essentially learning a behavior in simulation. So here we give the robot in simulation the task to reorient itself, basically perform an attitude control task, and only have the legs available. So you can see that it starts to do this interesting motion with the legs to change its body. We can transfer this also to the simulation environment of the actual system. And more importantly, we can also show that this works in the real world on the robot. So then in simulation, you start to see also very interesting emerging behavior. So this is something which is very difficult to do with classical control, where the robot is trying to land and even exploit small contacts with the ground in order to stabilize himself with respect to the ground. And then we performed the same experiment that you saw before, but now there is no reaction wheel attached whatsoever. So the system is really just purely using its limbs in order to do this reorientation task. And in order to show that this is also rather robust, we performed this, of course, several times to make sure that, that we don't have any failures during the experiment. But this is not all, because we see other challenges, and this is related to the environmental, the planetary environment. So here we have sand, it's very fine-grained soil, is very difficult to traverse with wheels because you can have this effect of getting stuck. And in some cases, this is also the end of the mission. So it's a very dangerous type of environment. But it's not said that with legs, you ultimately solve everything. So with the system that we had in the beginning, we also had this issue that we're sinking quite a lot into the soil, and thus reducing, for example, the efficiency and the safety that we want to have. So we developed a new type of foot, basically for planetary exploration, which is this, what you see here. And the main focus here is to reduce the sinkage that you can have in the soil, but at the same time have a high traction. So that's why we also see these grouses. So we cannot not just mount the plate because it has to somehow adapt to the ground. So we also introduce a passive degree of freedom on the ankle, so that has the opportunity to adapt to the terrain. Now, of course, in space research, it's very important that you somehow validate this in some environment which is representative. So we went here, it's Ruag, Switzerland, who have this sand pit, which is having a Martian soil simulant inside. So not from actually Mars, but simulant that has the same mechanical properties. And here we can show that it's possible for the robot to go up and down all those slopes, basically the maximum of the test bed, to demonstrate that the leg system is capable of climbing slopes that you would potentially encounter also on Mars. After these experiments, one of the findings is also the energy consumption. So we recorded basically how much energy are we using with respect to the slope that we see on the soil. And as I mentioned in the beginning, you can make use of different types of locomotion pattern, of gait patterns. And we can also compare those and find the ones that have the least energy consumption for a certain type of inclination. So once you do this, once you extracted these energy curves, you can actually perform what is called path planning on another planetary body. So here we chose an exemplary crater on Mars, and we basically simulated a mission scenario during which you want to go from a position outside of the crater, maybe this is where you land, inside the crater to perform some investigations, and then go out again. And thanks to those efficiency curves that we have derived on the test bed, we can find an automated way to basically plan the perfect trajectory that the robot has to do to perform the exploration. And for us, this is very interesting because it shows us how much energy does such a system potentially need in the future, and we can design the system accordingly. So talking about future missions, what are the things that we have in mind? So here we see an area on the moon that is of very high importance, is the Aristarchus Plateau in the equatorial region, because it's very geologically very diverse area. So we have this crater, which is rather young, and the collapsed lava tube, and this is some very scientifically interesting area. But if you look a bit closely, we see that it's very challenging terrain to move with a potential wheel system. So here we see that, okay, this could be the perfect spot to try out a new technology like a leg robot. So we have started to develop some concepts and see like how can we transfer the spacewalk robot that you saw in the beginning into an actual space exploration robot. Of course, you have to add means to produce energy on board. So you have to add solar panels, you have to add like some sort of thermal management. And then you want to also have some payloads like a spectrometer and a microscopic imager. So this is currently the work that we are doing and seeing like how can we transfer this technology to an actual space mission. So and then lastly, just to show the work that we've been doing at the Robotic Systems Lab over the last decade. It started with this terrestrial robots in 2012, up to the product that you can buy now from Anybotics. So it's a commercially available inspection robot. And then in the meantime, we start to develop also the space robots. And hopefully, at some point, maybe in the 2030s, we would see this on the moon or Mars. Yeah, with this, I would like to finish. Thank you very much for the attention. I hope you will enjoy the robot, and I'm very happy to take any questions.
Thank you very much, Hendrik. That was a very fascinating presentation. I would like to invite our online viewers to ask questions through the chat box. And I would also like people in Japan to ask questions in Japanese. So if you would like to type in your questions in Japanese, this is also very, very welcome. First, I would like to perhaps, in the meantime, call on our audience at the venue if people have questions or just an impression or comment on what you have just seen from the two presentations. And very simple questions or comments are very welcome. Please raise your hand and someone will be with you with the microphone. I see some I see some people discussing questions. So if you would like to share with us.
動力源とそれをフルチャージしたときに稼働できる時間、あと先ほど今後のソーラーパネルがついたのがあったんですけれども、それと例えば既存の動力源は同時に使えたりするのかとか、その辺のところが知りたいです。
Thank you very much. So the question came from the Tokyo venue. This is for Dr. Hovenbach, for Hendrik, about the spacewalk. The question is, she would like to know how what drives the motion or the motor of the spacewalk, and how long it lasts. And the second question is, there was mention about the use of solar power for the spacewalk, and how will it be combined with the current drive? I know the answer, so I don't know how to pronounce it. But not pronounce, but yes, how the driver of the spacewalk.
Yeah, thanks for.
Does that make sense?
Yeah, I tried to answer this question. So currently we have those the motors in the hips So there are 2 motors per hip and then 4 legs in total, so 8 motors. Inside the robot, there's the motor controller to perform this locomotion. So those are brushless DC motors. And currently, the robot that you see there is all battery operated. So here the lifetime is rather short. So we see something around 2 to 3 hours. But when I showed you these energy curves in the presentation, we also estimated how much energy would you need on another celestial body. So the good news is that if you go down with the gravity, you also require less energy for locomotion because you don't need to spend the weight of the robot. So basically, it feels a bit lighter, so the forces are a bit lower. But then to generate energy, we did this concept study for the moon. So the concept I showed was for a lunar environment. And we realized that with these, you can actually traverse during one lunar day, not continuously, but you can basically during like a 10-day mission traverse with a solar panel of this size. And the exact like length of the traverse highly depends on the terrain that you walk through. So if you go a lot of basically up and down on the way, then you would realize that you cannot go that far. But basically, we look at mission traverses of a couple of kilometers. I hope this answers the question. If not, please ask again.
Actually, thank you very much, Hendrik. Actually, my translation was bad. She wanted to first know what the power source was.
Okay, yeah. The power source is a lithium polymer battery. So it's just a normal big battery inside the robot.
Thank you. Thank you very much. We have a second question from the online viewer. Thank you for the amazing presentations. And again to Dr. Holvenbach, what is the autonomy of Spacewalk?
Yeah, that's also a very good question. Thank you. So for the experiments that we performed here, the robot was mostly teleoperated. We did some investigations where we performed like a semi-autonomous approach, basically where we give the robot waypoints, and then it had more sensors on board to perform like automatic path planning along the way in the environment. But the autonomy level basically at the moment is still rather low. But we have other robots here in the lab, the animal robot, where the autonomy level is much higher. The main idea of the Spacewalk platform was investigate really the locomotion concept, but then we have the capabilities here to also add higher level autonomy on the systems.
Thank you very much. I still invite questions, if I may. And since this is a science communication project, please ask very, very simple questions. Our speakers are very knowledgeable, but they are also very kind to answer any question. For example, I had one before I heard one before the event started that was wondering where the Spacewalk has been so far. I know it has been to Tokyo.
Yeah, I mean, it was developed in Zurich, Switzerland. We also performed these experiments in the sand pit here in Zurich, which was a very lucky coincidence that not very far from here, just a few kilometers, they have this test facility. And when you saw these experiments on this flat floor, where it was moving freely, there it has been in the Netherlands at the European Space Agency. They have some test facility for low gravity experiments. So it has been to the Netherlands. But it then also has been at some congresses, for example, at the International Astronautical Congress in Bremen and at the European Rover Challenge in Poland. So it's traveling quite a bit, I have to say. Even during Corona times, it managed to get to Tokyo.
Next time, hopefully with you. So that was questions on the Spacewalk. If also we would like to show a close-up for our online viewers, perhaps. In the meantime, would someone like to ask about the Tranquility base escape game? Any questions from the audience? Or just your impression of how it was to experience the demo? Can we have the microphone, please?
日本語でよろしいですか。宇宙の、使われている、色、日本からとか、世界中から、ISS とかの機材とか、あと宇宙ロケットとか、宇宙服とか、今回の、折り紙ロボットも、色が、ホワイトカラーだったり、銀色だったり、光を跳ねるようなお色が多いのに、今回、スペースボックが黒いお色なのを、すごく、いつもは銀色だったり白い感じなのに、なんで黒い色だったり、あと形とかも、今回その形とかお色で、何か特徴があるのかなっていうのをすごい思いました。
Thank you very much for your question. The question goes about the spacewalk, and she is wondering, normally in outer space, she sees many equipments or also spacesuits that are normally in white or silver. And many of the things, or most of the things that she has seen are in these colors, white or silver, that reflect light. Also including the origami robot, the Mori module. However, the spacewalk is black, and it also has a very specific shape. So she would like to know why the color black was selected, and also if there are the reasons behind this characteristic shape.
Yeah, thanks for the question. It's true. Yes, this is a good observation. The thing is, the robot here is not space graded in no means. So this robot will not survive if we send it to space. The reason why it's black is mainly from the carbon. So the shell of the robot is made of carbon fiber, which traditionally is black. And we just we didn't change the color to something else like white. But yeah, if you wanted to send it, then you have to most likely apply some sort of coating, also even change the type of material that we used for the shell. So the shell basically is a design choice. So we wanted the robot to be as compact as possible, so that we don't waste too much mass on like having shapes that we don't use. So it's very packed inside, and then we just made a very quick design overhaul to make it look somehow nice and not just as a box, and that's where the shade comes from. But the future system will most likely not look like this, more like the concept drawing I showed in the presentation.
Thank you very much. We have another question from our online viewer to the spacewalk. Are there any measures taken to protect the spacewalk from the regolith, or I hope I pronounced it right, the sand on the lunar base, or excuse me, the lunar surface, sand in the rock on the.
Yeah. This is the environment. The regolith is very challenging one because the dust managed to get everywhere, and if you're moving parts, it's a huge problem. So the robot that we have now has very minimal means to survive in environments like this. It was operated on Earth. So here we installed filters and added some ceilings to make sure that no sand is ingressing into the robot. But for making this an actual space probe, there's way more work to be done on this. So I just want to emphasize that this is still a prototype that has been developed to investigate different concepts. But to actually make this a space-ready probe, there's really much more engineering that still has to be done to make this ready.
Thank you. And I have one last question for Alexander. So, what inspired the tranquility based scenario? Was it science? Was it a movie?
Thank you, Kyoko. That is a good question. Actually, both of them, not really a movie, but classical, how to say it, a dramatic space movies where everything goes bad on a base or something like that. I'm thinking about Apollo 13, the movie. So we wanted something a little bit close to that, but more scientific accurate. Yeah, we really wanted to input real scientific data, like as I said, for example, the placement of the lunar base, or and also using research device by giving them an applications which also add scientific content. So in conclusion, I would say kind of Apollo 13, but more scientifically accurate with real stuff.
Thank you very much. And I think that you reflect the very, very core of this EPFL virtual space tour project, that it is a science communication project. We do feature real science, not only from EPFL, but also from other Swiss partners. And it is for everyone to enjoy real science. So, and I must add that that was a question from our English channel viewer. So thank you everyone for all your questions. We will take a 10-minute break now before we move on to the second part, which will feature space debris problems. And we will hear from academic and industrial speakers. So please stay tuned if you are online. And we hope our audience in the Tokyo venue will also join us for the second part, which will start in about 13 minutes. Thank you very much, everyone, for coming. And we look forward to seeing you for the next session. Thank you. Good evening, everyone in Tokyo. Good afternoon, everyone in Switzerland and Europe. And perhaps for some viewers joining us elsewhere, possibly good morning. My name is Kyoko Suzuki. I'm the head of the Science and Technology Office Tokyo at the Embassy of Switzerland in Japan. Thank you very much for joining us for the EPFL Virtual Space Tour in Tokyo. This is the session 2 of today's talk event. And for those of you joining us today, excuse me, for those of you joining us from this session, I would just like to repeat shortly that the EPFL Virtual Space Tour is organized by the EPFL Space Center at EPFL, Swiss Federal Institute of Technology in Lausanne. It is a science communication project that centers around 2 brand new projects. So one is the Virtual Reality Universe project from the Laboratory of Astrophysics, LASTRO. It uses virtual reality technology to bring you through a journey in outer space using the most detailed map ever known to us. We have here in Tokyo, Midtown Hibiya, Base Q, the virtual reality goggle version demo. So if you are in Tokyo, please come and visit us. We are here until tomorrow. We also have the virtual escape game Tranquility Base that was newly developed for this world premiere EPFL Virtual Space Tour project. And it started out as a physical escape game called Switzerland, We've Had a Problem. However, due to the pandemic, it was not very easy to have people gather and enjoy this escape game. Therefore, the Student Association Space at Your Service developed an augmented reality version. And this is the world premiere of this very exciting escape game. If you can come and join us, again, we are here until tomorrow. If not, please search for Tranquility Base. It will be in your App Store or Google Play, and you can download it on your devices to play. So those are the 2 major projects or the 2 core projects of our EPFL Virtual Space Tour. And also, we are very pleased, we are very honored to have a very strong talk event that goes together with these great demos of the VIRUP and Tranquility Base. And today, I'm very proud to present to you wonderful speakers for the space debris problem, monitoring and solving it session. So without further ado, I would like to call on our first speaker, who will explain to us why space debris are a problem. To explain to us this very hot, new, and challenging topic, I would like to invite Professor Thomas Schildknecht, Vice Director of the Astronomical Institute of the University of Bern. Professor Schildknecht.
Thank you very much for the kind introduction. Good evening, everybody in Japan. Good afternoon, good morning, wherever you are. So I would like to give you a brief introduction into the problem of space debris and show you a little bit how we are observing space debris and characterizing this debris in Switzerland. So what I'm going to show you here in this short video was a wake-up call. You may know this collision between an active spacecraft and a decommissioned spacecraft on the 10th of February 2009. The fact that 2 spacecraft collided in space was surprising to the public, but What was more severe is actually it produced thousands of debris. And as you see in the video here, these debris stay in orbit and they filled an entire shell around the Earth. Even nowadays, many spacecrafts have to do avoidance maneuvers to prevent a collision with one of these debris. So what do we know about the debris population today? We know that there is about 35,000 objects larger than 10 centimeters in space. About 25 to 30,000 of these objects we know by name and we know their orbits. But there is much more up there. There is 60,000 pieces larger than 5 centimeters, and there is of the order of 1 million objects larger than 1 centimeter. So the question you may pose is, why is 1 centimeter a problem? Problem is that the velocity of these objects is so high that if a 1 centimeter piece collides with your spacecraft, it will release the energy of a hand grenade. And it's not really a good idea to let a hand grenade explode on a delicate spacecraft. So this is the real problem. Why do we care? If you are an owner operator, you care about safety of flight. You want to prevent collisions. If you are a designer of spacecraft, you care about risks. You want to know, can I do some shielding? Mission analysis wants to come up with the best trajectory to reduce the risk. And governments, space agencies, and scientists, as I am one, we care about protecting vital services from space. We care about the long-term evolution and the long-term sustainability of outer space activities. What are the questions we are coming up in when doing space debris research? First of all, very simple questions like, how many of these objects are up there? What's their size distribution? What are their orbital regimes? What's the nature of the objects? Sources, sinks, physical mechanisms, how are they created? How are their orbits going to evolve? And what's the long-term perspective for this population? All that needs observation. So we first search for debris, we determine their orbit, and then we characterize them. We use in Switzerland the Swiss Optical Ground Station and Geodynamics Observatory in Zimmerwald, which has a whole suite of sensors and is operated 24 hours, 7, all throughout the year. We have sensors of very different types. On the bottom right side, you see our workhorse, a 1 meter telescope. On the left-hand side, an 80 centimeter telescope. We do also some research on behalf of the European Space Agency with their 1 meter telescope in Tenerife at the Canary Islands. We do optical observations, but we also measure distances in order to improve the orbits of these pieces using a laser ranger. What you see here is not a Photoshop picture, but it's a real image of our laser ranging equipment during nighttime. And I have a short time lapse to show you how we range one object after the other throughout not just the night, but 24 hours. These measurements are providing us better orbits finally, and better orbits are used to prevent collisions, warn operators so that they could do an avoidance maneuver if necessary. So what do we know? On the left-hand side here, you see the catalog, the best, most comprehensive catalog in the world at a certain point in time. On the right-hand side, you see superimposed debris objects, which we have been detecting here in Switzerland together with colleagues all over the world. So be aware that what you have in the official catalogs of orbits of natural or of artificial objects in space is not the full truth. And this population of these green objects here actually are debris pieces which were created during an explosion of an upper stage. You see here a series of exposures from our observatory, and probably I hope that you see these small dots all over the place, dozens and dozens of small objects, small fragments. The trails here, these are stars. That's not the objects we are worried about. So what you see in this picture is 3 clouds of debris from 3 different breakups. They happen still several times a year. And it's really important to find all these pieces in order to protect active spacecraft. So all this is only possible through international collaboration, and we collaborate here with many space agencies, the European Space Agency, with NASA, with JAXA once in a while, and with Russian colleagues. And at least the same importance should be given to the international organizations where we try to come up with rules for mitigating and really preventing space debris in space. One of them is the United Nations Committee for Peaceful Use of Outer Space, where there is a working group on long-term sustainability of outer space activities. Another one is a more technical group among all, or comprising all the major space agencies, where we discuss technical questions concerning the space debris environment. So, take-home message. We need collaborative, international, and a holistic approach to address the space debris problem. We need to work all together to better characterize that problem. And space debris research is providing the scientific foundation for sustainable use of outer space. With that, thank you for your time.
Thank you very much, Professor Schildknecht, for taking us, giving us an insight into the world of measurement and space debris. And it was very fascinating to see these. I would like to remind the audience that we will have a questions and answer sessions at the very end. So if you have questions, please put them in the chat box if you are online. And if you are in the venue, please remember them so that you can ask them later to our speakers. Thank you. And I would also like to invite our Japanese audience online to send your questions in Japanese. It will be translated, so please type in Japanese as well. And so thank you, Professor Schildknecht. And I would like to move on to the next presenter, who will give us, now that we know, now that we have seen why space debris are a problem, what is actually being done currently? What are the things that are actually taking place and in the near future? So we'd like to invite Dr. Luc Piguet, co-founder and CEO of ClearSpace, which is an EPFL startup that is one of the very first companies to tackle this challenge. Dr. Piguet?
Thank you for having me. So my name is Luc Piguet. I'm the CEO and one of the co-founders of ClearSpace. Today, ClearSpace is a team of about 50 engineers, well, mostly engineers, and we work on developing solutions and services that we believe will enable a thriving, resilient, and overall sustainable space industry in the future. The situation in space, and I think Dr. Schildknecht presented it very clearly, is getting worse over time. We have more and more debris and objects in orbit, which present major risk and issues for operational spacecraft. Our focus is looking at non-functional objects, derelicts that are in orbit, like non-functioning satellites or uncontrollable satellites or rocket bodies. And today we have, based on the estimates of a study by Darren McKnight, There's more than 5,000 complete non-functional objects, and that excludes all the pieces of fragments and debris generated by fragmentation of it. And over the last 20 years, every single year, we've been adding 74 new ones. And if we can give a comparison, today there's about 3,400 live satellites. It's like if the space industry was a high-speed motorway network without any tow truck service for many years. So for us, that became a realization when we worked on the problem at EPFL. We came to the conclusion that it is our responsibility now to build the first tow truck, or to build a tow truck to be able to serve those satellites, those objects in orbit, and to be able to build up a sustainable environment. So when we look at the future, what is really necessary to make to enable a sustainable area in the space operation? The first one is technology development, and that's where we're focusing on. The other one is obviously you have to find or develop business models which are viable to finance that kind of services. And the third one is obviously you need national policies, international coordination, you need standards and guidelines. There's a lot of work that has been put into those dimensions already. What we have been working on at ClearSpace after the foundation, we have been selected by the European Space Agency to lead the first mission to remove a piece of debris belonging to the European Space Agency that has an objective to fly in 2025. When ESA issued this mission, their idea was we have to create the first example. We have to make the first product or the first tow truck to demonstrate that the complete value chain of removing space debris is feasible and can be viable, and open up by this a new industry. A little like you have on the motorways, you have car support services. There's no reason why we wouldn't have that kind of services in orbit. So the ClearSpace One mission's objective are one, to remove an ESA-owned derelict object mass greater than 100 kilograms with a flight in 2025, to demonstrate in orbit feasibility of critical technologies which are enabling other in-orbit service opportunities, commercial opportunities. Three, provide a robust business model for in-orbit servicing activities beyond the service, and then comply obviously with ESA space debris mitigation requirement, because we don't want to produce more debris. So this is a mission that has relatively simple objectives, which obviously go down into much more detailed mission objectives, which have much more requirements. The mission is in its initial development phase. It's supported by 8 European member states. And the object we're going to pick up in orbit is the Vespa upper part, which you can see in this animation, which is this cone that is in orbit. ESA has a couple of those in orbit today. It's a good example to demonstrate the complete value chain using an object which is relatively sturdy and doesn't present a high risk of producing more debris. It's got the advantage also that it's got the size of the representative of small satellites, which is the tendency of what we will find more and more in orbit. When we look at the future, I think at the challenge, we think there's 2 dimensions that have to be addressed at the same time. One is making sure that we address the past, so those 5,000 plus objects in orbit that require service, and then at the same time build up something that is sustainable for the future, and means addressing the case of new constellations that are coming into orbit, and that will come into orbit over the coming years. And on this graph, what you can see is on the horizontal axis, the inclination of the orbits of those satellites, how inclined they are compared to the north-south pole axis. And on the vertical, you can see the altitude where the satellites are. And I think one important element there is that depending on the altitude, a satellite or a derelict satellite that's uncontrollable remain more or less time in orbit. And typically, as soon as you're above 600 kilometers, you can expect that the satellite's going to remain in orbit more than 25 years. And the time in orbit accelerates very rapidly. In some orbits, over 1,000 kilometers, it's going to be more than 1,000 years in orbit. And this means that the liability and the risks that are taken on those platforms just integrates over time and become on long-term unbearable. So those are typically orbits where services are needed. And we are working on the non-cooperative approach to being able to capture an object that has not been prepared for capture in orbit. Many of the ones that are up there already are in this situation. But then we think that the industry will develop little by little toward docking interfaces, which will simplify that kind of services in orbit as we have it on the road typically. So there's another dimension to what we do, is the fact that essentially space debris is a challenge that really transcends borders, continents, and application, right? Commercial satellites coexist with military satellites, with governmental satellites in the same orbits, the same locations, and satellites from different countries coexist in the same space. And this means that this is really a global problem that can really only tackled if everybody collaborates. Our approach to this is that we obviously want to build a sustainable solution, working with due regards to water, minimizing debris generation, interference, collision risk, and operation transparency. To make it really clear that what ClearSpace is doing is build up a sustainable model with objective to create a sustainable environment where future generation can strive. So really what gets us out of why we do what we do, what gets us out of bed every morning and gets us to work many hours and late hours, is because we believe that removing man-made space debris is a responsibility of our generation, right? And if we can do what we do today, it's because before us, there have been generations of space engineers that did miracles in the past, and we can build on technologies and experience they have actually accumulated to build the services that will make the next generation capability or possibility to continue benefiting from space and reality. And this is really what wakes us up every morning. And this is really what motivates our mission and what we do. Thank you for your attention.
Thank you very much, Mr. Piguet. Now I would like to turn to a concrete also example from Japan on the tackling the space debris problem or challenge. Mr. Chris Blackerby, COO of Astroscale, will also introduce to us his activities or their company's activities. Mr. Blackerby?
Thank you. You can hear me okay?
Yes, very clear.
Great. And I assume you can see my screen.
Yes, maybe you want to make it present. Yes,
That's
perfect.
Okay. Great. Well, thank you. It's great to be here. I am in Tokyo. Unfortunately, I'm not able to be there in person. I very much regret not being able to join everyone here. I'm only a few kilometers away from you now, so it's hard for me to not be there in person. But thank you for having me here remotely. I've been on panels before with Luke from ClearSpace, and it's always great to hear him talk. And every time I do, I'm always reminded about how aligned we are in our concepts and how much we agree, and our talking points are similar, and our vision for what we want to do about orbital sustainability is so aligned, and that's fantastic. To me, it shows that there is a clear recognition of the issue and a multiple groups that are looking to solve it. So it's really heartening to see Luke give his presentation again. So it was really great to watch. So mine is going to have some repeats from what we heard from Luke and Dr. Schlittnick earlier. It has a lot of the similar concepts, but we are a company as well, like ClearSpace, that is looking to solve the sustainability orbital debris problem, and trying to do it as a private sector company, not as a research, but as a company that has brought in investment and is looking to solve this as a business. So as we heard from the previous speakers, our orbital environment is already at risk. And we are talking primarily about two different orbits. Now, there's several orbits. As was discussed earlier, there were breakups in the highly elliptical or HEO orbits, which is a little different. But the two main ones that we Astroscale are focused on are LEO, low Earth orbit, and geostationary orbit. And LEO, the low Earth orbit, about 200 to 2,000 kilometers, that's where we're seeing a lot of the recent developments in commercial space. These large satellite constellations where companies are launching hundreds or thousands of satellites, they're going into these LEO orbits. And traditionally, they've been more in terms of measuring Earth science and taking pictures of Earth and measuring the climate. Lately, there's been a lot more that do communications as well, like SpaceX, Starlink, and OneWeb are two of the biggest ones doing low latency commercial communication satellites, which is something that we are going to be needing and using for everything that we do. So many aspects of our lives are supported by data we get from satellites, and it's just continuing. And low Earth orbit is where we see a big increase. The other orbit that we're focused on is geostationary orbit, which is farther out, about 36,000 kilometers altitude. And there, the satellites are mapped, targeted to the rotation of the Earth. So they rotate as the Earth rotates. They're much bigger and they're much more expensive. But out there, we're focused on making sure that those satellites are serviced as well. So those are the two main orbits that we're looking at, and both of them are quite crowded. And as was presented by our previous speakers, this increasing number of satellites leads to the potential for more debris, which leads to the possibility, the definite next step of more risk. So the more satellites that are up there, there's obviously going to be more risk. And then once a debris incident happens, we're going to see even more risk. Avoiding those smaller pieces is going to get more and more difficult. And as more collisions happen, the usability of the orbits becomes very difficult. And if we can't use them, then we can't benefit from them. So we need to solve this environmental problem. And really, it's like orbital highway safety. And Luke used the same metaphor, the same example, talking about our orbital highway. And that's really what we're trying to protect. And the way we see it is that space environmental management is necessary to support servicing and the safety of operating satellites in orbit. And just like we have road traffic management, just like we have rules of the road where there's traffic and motor vehicle acts, we need space traffic management to have norms and guidelines and best practices. We need to focus on that, and those don't really exist in enough of a that as they should. We also need understanding of what's up there, awareness. So we have road monitoring to understand where traffic is and where you should avoid, what roads you should take or shouldn't. We need that in space situational awareness. And that exists to a degree. Again, as was discussed by previous speakers, we are monitoring a lot of that and we can understand a fair amount, but there's more that we can learn. And so we want to be able to measure that even from space. And then going further, we need to do the servicing. We need to go up and be able to remove the debris, but also to do other things for satellites, repair them, refuel them, move them from one orbit to another. There are so many different possibilities that can be implemented once we develop some of these technologies. And so astroscale, again, I keep referring to previous speakers because so much of what we're saying is in line with each other. But just like Luke said that this is a global problem that needs a global solution, astroscale is a global company. We have over 200 team members in 5 offices around the world. And we're trying to focus on all of the issues that are necessary to solve this problem within these offices. And these issues to solve the problem, again, as you heard earlier, you see the same thing. We are needing to develop the technologies. We have primarily engineers on our team, about 70%, 75% are engineers, but that's not the only thing we need to fix. We need to find the business case and find the customers, and we need to get the policies and best practices in line. So we need to work with governments. We need to work with international organizations. We need to get out there and spread the messaging about the importance of this issue so we can get funding and policies put in place. So as for what Astroscale is trying to do to address this problem, we really have 4 main business lines. And each of those business lines addresses one aspect of what I talked about. So starting from the left, the first one is end of life services. And this is preparing satellites before they launch to be removed at some point in the future or to be serviced at some point in the future. Right now, we're looking at removal. And so we're talking about putting a docking plate, magnetic surface docking plate onto satellites before they launch. And then when they need servicing, we can launch something to attach to it and bring it down out of the way. That makes it cheaper for us to develop. We can predict what we need to build. That makes it a much easier path toward a market solution. The next one is active debris removal, going up and removing, just like ClearSpace is planning to do with that upper stage, going up and removing a piece of debris that's currently up there. We can't use a magnet to do that, so we need to develop different types of robotic grappling fixtures, and we're developing those in-house right now. So that's the second business line we have, and we have a mission right now with the Japan Space Agency to start to work on that, to observe some satellites, debris, upper stage debris in orbit. The next set is in situ space situational awareness. So I talked about getting a better picture of the orbital environment. We want to be able to launch a satellite up and take pictures in situ, in orbital, in the orbital highway to understand what's up there. There is interest from a lot of governments to do that. And then the last business line is in the geo belt, the one farther away that I mentioned with the really big, expensive satellites. We have a business line to go up there and repair those satellites and extend the life of them. So those are our 4 main business lines where we're looking to be able to solve this problem. And we're already started doing it. We have a satellite in orbit right now called ELSA-D, and we launched it in March. And a couple of weeks ago, we did the first test. So we separated 2 satellites in orbit, and then the larger one you can see on the left moved in and captured the smaller one. So we demonstrated that we can do the technology to release and capture a satellite in orbit. And we're going to do a couple more tests like this over the next few months to prove even more difficult steps to do these captures. And companies are starting to pay attention. So OneWeb, a company that builds a lot of satellites that launches many satellites into low Earth orbit, is putting a small docking plate on all of their satellites. And this docking plate has a ferromagnetic surface. We helped design that surface that you see in the blowout, so that they can be, when we send up a satellite, we can be compatible with capturing onto that. So OneWeb, this docking plate doesn't help OneWeb's business at all. It doesn't help them with their business of communication. But what it does, it prepares them to be serviced in the future. This is a fantastic step that companies are looking toward preparing for servicing going forward. As for the active debris removal side, that's the stuff that's up there right now. It's the stuff that ClearSpace and Luke are focused on doing. We need to get it done, and we need to make sure we address this immediately. If we don't, we can see the increase of having no mitigation over the next several hundred years. We need to start preparing satellites for being removed. We need to go grab the satellites that are up there, or grab the debris that's up there and bring it down. Experts say that about 5 objects per year. If we can remove about 5 objects per year, we will massively reduce the risk that currently exists in orbit. So the bottom line, back in September 1957, before Sputnik launched, this was the number of human-produced objects in orbit, basically 0. We weren't getting any benefit from them, but there was no risk. Now we get a lot of benefit, but there's a lot of risk. So we're at the place now where we need to protect the benefits that we're getting from those satellites in orbit, start reducing that risk as soon as we can. Thank you.
Thank you very much, Mr. Blackerby, for the very comprehensive and concise presentation. As a non-expert, it is really eye-opening and also reassuring that this challenge is really being tackled in our times. And thank you. Now, I would like to turn your attention to our speaker at the Tokyo venue, who has kindly joined us, Professor Shinichi Kimura, Faculty of Science and Technology at the Tokyo University of Science. is here with me today and will present to us why it is so hard to solve this challenge of the space debris.
Okay, yeah. Okay, thank you very much for a kind introduction. And good evening, ladies and gentlemen. My name is Shinichi Kimura from Tokyo University of Science, and it's a very great honor to talk here and participate as such a great talk on the space debris. The other day, Ms. Suzuki gave me the very exciting title. Why is it problem is difficult? I'm curious. First speakers point out what is the problem, and the second and third speakers are taking actions. But from the technological aspect, it still has a very difficulty to realize that. Therefore, I'd like to discuss with you what is the next step, what to say, how we proceed in the technological areas. Why the specific mitigation is difficult? I think the problem is we need to find and capture the target debris and under the ambiguous situations. When we capture or to say mitigate the space debris, we need to mitigate the whole process nearly blinded situations. Therefore, we need to get a certain autonomy there. I think technical challenge for this is I can summarize the 3 points. One is the dexterity to capture the in nearly so say ambiguous and blinded situation, capture the targets safely and reliably. The second is autonomy to access to the targets safely and reliably. And third is the simulations. I'm going to talk on these points, and I'd like to discuss with you, and I really hope your idea to overcome these points. The problem is this viewer shows the typical sequence to mitigate space debris. First, the chaser satellite or the mitigation satellite is launched to the rocket and access to the target around and captured and re-enters. A very simple so the scenario. But in the situation to realize to that that access to target, I'd like to point out at this point, 2 points, access to the target and captures. The problem is we need to realize this process in nearly blinded situations. I have participated research on the space robotics and space debris mitigation areas for years, and I participated world first robotic satellite called the Engineer Test Satellite 7. And in this case, the satellite can communicate in the 40 minutes per pass. And we only have the 7 chance to connect to the satellite. But this satellite is a rather luxurious because this satellite can communicate, utilize the, through the data relay satellite. In the case of the direct communication, the communication period is only the 10 minutes per pass. And we only have that 5 or 6 times per day. Therefore, that is, in a sense, the satellite need to other time, 15 minutes per day. Other of this period, satellite need to autonomously operate it autonomously. Under that kind of situation, we need to establish a kind of dexterity to capture that under the ambiguous situations. As for space robotic areas, Japan have the, some, so say, achievements, and we already launched robotic satellite in 1997. The world first robotic satellite is called the Engineering Test Satellite 7. And we also launched manipulated flight demonstration mission on the special. Of course, we come to the space robotics is coming to the mature, but these satellites can only capture the this kind of handles mounted on the targets, and dexterity is a very low level. Therefore, we need to capture the uncooperative target. That means the target satellite without any handles, as Chris mentioned in the previous presentations, and maybe the target satellite not controlled and maybe rotated. And in this point, I really hope to overcome this problem, Clean Space and the Astroscale, and in their strategies in near future. Even if we establish that this kind of dexterity, we also needed autonomy because we cannot communicate with the chaser satellites in a limited period. Therefore, the target chaser satellite need to autonomously find the target and decide what to do in orbit. Therefore, we need to establish a high performance image acquiring and processing unit in orbit. But that the space debris is, in a sense, the, considered as a industrial waste. Therefore, no one will hold for that. Therefore, we need to establish a very high performance and autonomy on orbit in very low cost. Therefore, we focus on the utilization of the commercial off-the-shelf technologies, not only the devices, but also the softwares. We developed this kind of intelligent cameras, and we call it microbrain, and utilizing the commercial off-the-shelf technologies. And we already succeeded in the captured this camera in operated in orbit. Maybe the images of the Icarus or the Hayabusa 2, these images are captured by this camera. We really hope to utilize this kind of technologies for space debris mitigations. And as mentioned in the Chris, the Astroscale already launched ELSA-D missions this March. Our camera is successfully launched together with this satellite, and I heard that is successfully working in all. So I'm really curious on the result of these missions. And in addition, we cooperating with the Swiss on this kind of technical area, cooperating with EPFL and Dr. Madi and HSLU, and we include the Japanese partner, the Nikon, to establish the on-orbit autonomy to realize such complicated missions. The third point I'd like to point out the simulations. Even if we establish some kind of the autonomy and kind of dexterity, we need to qualify before the launch, or to say we need to simulate validate that kind of technology in various situations beforehand. And that means we need some so to say flexible and realistic simulation. In the case of the Hayabusa 2 mission, and the so to say operation crew take many time and many rehearsal before the touchdown. Of course, Hayabusa 2 missions are complicated. They're very sort of cutting edge, but they also need that kind of preparation beforehand. We already kind of established a kind of the simulation situation, but I really, I think we really need simulation environment, such as your virtual reality and operational simulation system. Maybe that is a good cooperation for this area. On this point, I already published together with the friend of the EPFL this book, Space Debris Peril. So please refer this book for details. I'm move back to the point. We need to establish the dexterity and autonomy and simulation. But as for this kind of technologies, it's not only for the space, but also the autonomy. Maybe we can cooperate with the autonomous guidance navigation system go on ground, and dexterity is also needed in the terrestrial robotics and simulation also. So I hope to cooperate various technology on ground to overcome this kind. Thank you very much.
Thank you very much, Professor Kimura, for the very full presentation, giving us a lot of insight into a little bit more of the technological aspects of the challenges, and also introducing some of your collaborative work with Switzerland and some new projects. So since Professor Kimura touched upon the risks of the issue, I am very pleased to move on to our next speaker, who will give us an even bigger picture, perhaps also into with the Earth in the scene, about the challenges, how to make the risks or how to manage the risks at an international level. Our speaker is Ms. Marie-Valentine Laurent, Executive Director of the International Risk Governance Center at EPFL. Ms. Laurent, please.
Thank you. Thank you, Tokyo, for introducing me and for inviting me to this fascinating panel where we discuss both problems and solutions, which is quite unique. And that I find is really very reassuring about our ability to address the problem. That's very reassuring. I'd like to speak today about the governance of space debris collision risk, and highlighting that the governance, what we mean by risk governance is something that is more comprehensive than just risk management or risk analysis, and that it's a comprehensive approach towards assessing the risk, namely first identifying and assessing the risk in terms of probability and severity, but also cause, exposure, impact, vulnerability, and consequences, but also including the cost of this. And the cost of collision and the cost of mitigation, namely, in short, avoiding the creation of debris, and the cost of remediation, reducing risk from existing debris. Risk governance, of course, also includes management, which is composed of at least two elements: the technical solutions and the governance solutions. And the governance solutions include regulations, non-binding instruments, guidelines, code of conduct, industry standards, but also, and I welcome this, that was mentioned a couple of times today, to policy, from science to industry, between industry and policy. All this is very, very important. Now, moving to the space activities that actually lead to this question of debris problem. Well, they are significantly increasing from about 150 payload that were launched per year between 60 and 2010. We have now more than 1,200 in 2020. The space activities are also diversifying with both low Earth orbit constellations, but also in-orbit servicing, space tourism, and new space activities such as in-orbit manufacturing and asteroid mining could soon become the reality. The actors that conduct space activities are rapidly evolving. There is a growing number of countries that become active in space, with more than 80 countries that have at least one registered satellite in orbit, and a growing share of space activities are in fact conducted by the private sector, also quite new. So the space economy has expanded in recent years, with global revenues of the Space Act sector that were below $200 billion in 2005 and are now above $300 billion. And it is predicted to boom in the next 10 to 20 years. Various sources predict this to be in around $1 to $2.7 trillion in around 2040. So we have also important critical services that are delivered on Earth and that increasingly depend on operations in space. So operations in space are not just for space. What matters here is the relationship between space and the Earth. So near space has become a highly valuable resource used for navigation, communication, Earth observation, and other purposes. Virtually all societies have now become reliant on space-based services in a wide variety of domains, typically transportation and financial systems that are dependent on position, navigation, and timing services, Earth observation, satellites that are crucial for climate and environment monitoring, weather forecasting, resource management, and land stewardship. So all in all, it appears really that if there is a problem with space debris, we really have to address it. Satellites have now become key to improving the sustainability of so many human activities, and it also useful for monitoring progress towards the sustainable development. Assessing risk to space debris, as I briefly said in the beginning, is not an easy task. If we understand that space debris is a byproduct of space activities, and that, as said before today, they encompass a wealth of objects of different sizes, generation processes, and harm potential, with objects that can be as large as a rocket body or a defense spacecraft, or as small as paint flakes. And that with the current monitoring infrastructure, only space debris larger than 10 centimeters in low Earth orbit can reliably be tracked and cataloged. So we have difficulty assessing really. We do it, but we wonder if that's enough. The current response strategy is insufficient, and it's complicated because first, the evaluation of the response strategies, the possible response strategies, is complicated by I would say two main factors. The first is the uncertainty about the cost of the damage, cost of damage to satellites, and disruption of services that rely on them. And second, there is a lack of data to conduct cost-benefit analysis of mitigation and remediation approaches. We have technical ways to do it, but there is still a lack of information about really the cost-benefit of it. At the technical level, where we try to ensure both the near-term safety of operations and the long-term stability of the space environment, we need to rely on both mitigation and remediation. Mitigation first, it refers to technical procedures and requirements for operational spacecraft, and are aimed at reducing the likelihood that they become or generate debris. So this includes, for example, spacecraft shielding, collision avoidance maneuvers, post-mission disposal, and removing stored energy at end of life to limit the probability of an accidental explosion. On the side of remediation, we refer to methods aimed at reducing risk once the debris has been created. And this is what Astroscale and ClearSpace presented, including actively removing derelict objects from orbit or lowering the probability of a predicted collision by affecting the trajectory of one of two pieces of debris prior to the predicted collision time, and also upgrading derelict objects with collision avoidance capability. In terms of response strategies, we have also a number of possibilities on the side of governance, where we have, of course, the binding instruments of public international space law, namely the 5 United Nations treaties on outer space that were adopted in the 1960s and 70s, a long time ago, which do not address directly the space debris problem. So to address this gap, non-binding instruments such as guidelines, best practices, industry-led best practices have been developed with the aim of limiting the creation of new debris and reducing collision. However, it is, I think, commonly understood that overall compliance with these international agreed upon guidelines is low. So the current response strategies have a number of limitations. First, they address mainly the creation of new pieces of debris without tackling the legacy of derelict objects. Second, national policies are non-uniform and they do not always implement internationally agreed upon guidelines. And third, national requirements that require ex-ante measures to minimize emissions potential to create debris. Once in orbit, the policies in place only weakly incentivize operators to reduce the risk. Another way, there is a gap between what is required ex-ante and what is implemented back to expo. So we need new strategies for the future. And reinforcing the current strategy would involve, again, technical solutions such as those that are developed by Astroscale and ClearSpace, but also the strengthening of monitoring and tracking capabilities, and the adoption of more stringent technical requirements. In terms of, on the side of regulation and governance, we believe that there is a need to revise the international guidelines, especially in light of the large constellations being put in orbit. We also need to devise mechanisms to incentivize countries to adopt national regulations and to incentivize industry to abide, certainly, I mean, for sure, with the guidelines. And there are other things that we need to work on, but above all, and as a few other speakers said, collaboration and sharing of information between space actors, public and private, will be essential. And for example, we believe that collaboration at the level of development of national laws, like between what we call like-minded countries, such as the US, Europe, or Japan, would be welcome. And to conclude, I would say that the safety of operations in space and the long-term sustainability depend on 3 main pillars: the development, the implementation of effective and cost-efficient technology. Second, the regulation that provides red lines and incentives. And third, collaboration among space actors, such as the type of collaboration between Switzerland, Europe, US, and Japan. Thank you very much for your attention.
Thank you very much, Ms. Marie Valentine Florent. That was a very wonderful presentation that I feel brought us back to earth, down to some kind of a down to earth problems of this, the aspect of this challenge. So now we have heard from all of our speakers for this session. I would like to invite the audience to ask questions, if any, or questions or even your impressions. For the online viewers, please feel free to type in the questions in the chat room in English for the English channel, and in Japanese for the Japanese channel is very welcome. Would anyone from the Tokyo audience like to start? So we have one question. Thank you.
貴重なお話をありがとうございます。スペースレベル、宇宙のデブリの話と、海洋でプラスチックが流れてしまうっていう話と、これからの私たちにとって大きな問題というふうに、考えています。で、今日は宇宙の話で、まさにその海洋と例えて言うならば、衛星やデブリの溜まりやすい、集まりやすい、そういう空間というのが、先ほど先生のお話の中で600キロ、また地上から1000キロを超えたあたり、そのあたりに大きく大別されて集まっているというお話があったんですけれども、そういったたくさん固まっているあたりに対して、より細かく観察をしていく、そういった、技術的な方法というのがどういうのがあるのかなということと、またその高さではなくて、緯度経度ということで見たときに、特にその集まりやすいそういった軌道というものが存在するのか、そういったところについてもう少しお話をお伺いしたいんですけども。
Thank you very much for the question, and it was a bit long for me to translate, so I try my best. So thank you very much for the valuable talk to everyone. Today we heard about the space debris, and it reminded me of the issues with the plastics in our ocean. And I believe that these are two very major problems in our times. Today we are talking about space, and I wonder, similar to the plastics being concentrated in certain areas, are there any parts of the space where the space debris are concentrated? I believe in the presentations, I saw that in the 600 kilometer and 1000 kilometer orbit, there are many debris that are concentrated, but are there any research or efforts being already taken, perhaps also from a technology side, to tackle these concentrated areas, also to observe more in detail these concentrated areas, and also yes. So will there be such kind of are there already such kind of challenges that are being tackled or being taken on? And the second question, we talk about the height or the from Earth, where the space debris are concentrated, but are there also is there a perspective from the longitude and latitude that needs to be addressed? Are there any concentrations in this from this perspective? And are there efforts being taken on in this area? So Professor Kimura will first volunteer to give an answer.
So say observation, I'd like to ask the first speaker for guidance, but I'd like to explain about orbits. Your question is very good because in orbit, the orbit, worthy orbit is so say kind of limited, and suppose that geostationary orbit is one ring, simple ring. Therefore, all world satellites share the single link. So if maybe a collision occurred there, the problem is expanded all over the world. Therefore, the so to say, the orbit everyone wants to utilize is of course exists. Therefore, the satellites tend to so to say condense to the orbit that can be a worthy orbit. Therefore, as you mentioned that not only the height, we need to consider the as for orbit, not only the height and the inclinations, which plane is flying, and of course the altitude and some kind of other parameters. But in a sense, other if the two satellites flying other orbits are they safe? Maybe it's not, because two satellites may be cross-sect in accidentally. The collision is so say nightmare for the space debris program. How to mitigate and how to mitigate the possible reliable satellites first. That is a very important problem. And so say like you mentioned that the similarity with the plastic problem. That is very important. Similarity is that we need to gather all the sunlight, of course. But different point is at least plastic waste, we can touch it and see it and gather it. But in the case of space debris, it is very hard to access there, and how to capture it and how to remove it. All these processes still missing. Of course, some players are struggling on this, but we need to overcome this kind of problem. And therefore, at that point is very good, but we need to especially consider the specific program.
Thank you, Professor Kimura. May I also address Professor Schildknecht on the challenges in the observation side?
Thank you very much, and thank you for this very interesting, important question. As previous speaker just mentioned, there is concentrations, of course, at certain regions in space, and these are the regions which are the most valuable regions for certain type of missions. And of course, we are closely watching these regions with observations. There is one additional point which is important to mention. The most densely populated regions are in low Earth orbit, as we call it, so in altitudes between 700 and 1,000 kilometers. And many, let's say, observation programs using radars, for example, are concentrating on that region with a good reason. But as mentioned just before, in the geostationary ring, which is point of view of the density less populated, it's very important to prevent any collision there, because if a collision would happen there, this very valuable region would be polluted forever. There is no way that the objects from the geostationary ring would, let's say, enter the Earth's atmosphere naturally. And going up there, and I think both Luke and Chris could probably agree with me. Going up there and taking something down is very, very expensive, especially if these are small pieces. So we are, of course, looking at the concentrations. By the way, just as a little story, when we started in the early 90s to do these type of observations, we obviously concentrated the observations to these regions which are most populated, simply because we wanted to find as much as possible and make our, let's say, customers happy, which was the ESA, the European Space Agency at that time. The last question about concentrations in longitudinal concentrations. The answer is very simple. No, there is no longitudinal concentrations. So these objects are spread all over all longitudes. So there's not perhaps a concentration over Japan or over Europe or over the Pacific. Again, with one small exception, which is the geostationary ring, where in certain longitudes, there is many, many active satellites concentrated because, as you can imagine, these are concentrated mostly over the areas where the services are used, so over the United States or over Europe or Japan. So, but apart from that, there is no concentrations.
Thank you very much, Professor Schildknecht. If any of the other speakers would like to add a comment, please raise your hands.
Just a quick comment on my side.
Yes.
Yeah, just a quick comment from my side. I just want to remind there is no international system to assign orbits operators to commercial operators. And this may exist in other domains, but it does not exist today. So that is something that is being considered in order to reduce certain risks in certain orbits. But so far, there's nothing.
Thank you. I also have another question from the online audience, if I may move on. So, how does taking down 5 objects per year possibly be enough to manage a 1 million debris problem? I guess there are many answers to that question, but would Mr. Blackerby like to answer that?
I can start. I always would cede to the academics who are studying this numbers in more detail to speak up. But from our perspective, I'll first refer to one thing that Professor Slupik said. Also, the cost of removal is really high. The cost of going up to grab a piece of debris. What we're trying to do is talk about bringing down multiple pieces. So going up and grabbing a piece at a certain altitude, bringing it down low enough that it's going to burn up quickly in the atmosphere, and then raising our orbits again to go back up to a piece. It's hard to explain how expensive and difficult that is from a propulsion or what's called delta V, a change in velocity perspective, to go up and down like that. It just is so expensive. So the cost of removal, has almost been prohibitive up until now. Now we're working on technologies to make that more achievable. So removing those big pieces and multiple pieces with one of our servicers can be possible, leaning toward. Now, as to the question about the numbers, we're talking about removing, when I referenced that, it was 5 or so large objects. And when you reference the million, you're talking about all of the really small objects. And we are not talking about removing that. And the technical and the policy solution for removing multiple small objects is is frankly not possible right now. It's hard enough to focus on it when we're looking at removing the big objects. Grabbing and sweeping up the small objects, and then getting the people getting people to pay for that kind of mission is difficult. When we focus on a specific object, like ClearSpace is doing with ESA, there's a customer, there's someone who owns that object. We can identify that group and then go and get it, and that group can pay for it. The small stuff we can't. So if we can bring down some of that big stuff, we reduce the risk that it will turn into small stuff. So in English, we say the prevention is better than the cure. And so if we can prevent the big stuff from becoming small stuff, that's how we're reducing our risk. So again, I'll leave it to the others to agree or disagree with that. But that's the way we're looking at it from our business perspective.
Thank you. Since we started out in Japan, would Professor Schildknecht like to add something?
I fully agree with Chris' comment. I mean, removing the big objects is remediation for the long term. Now, it makes sure that they're not colliding and producing smaller pieces, which then could collide again mutually and produce what is called the Kessler syndrome, an exponential runaway of collisions and small size debris. And I think as a scientist, of course, I'm mostly concerned about the long-term sustainability. You know, what is the environment in 10 years, in 50 years from now? Can our grandchildren still, rely on space for their societies, for example, or go and travel there? So this is the point with these active removal of massive objects. And the small ones, Chris is completely right. They are still a risk and they're staying there. And we need completely different technologies to get rid of them. But again, the important thing is that we really, as you mentioned as well, that we take care now of avoiding this Kessler syndrome by removing a few of the largest objects there. And this, I think, I could come back to the previous question. I mean, where should we remove these massive objects? Exactly where there is a concentration of massive upper stages, for example, because there's the highest risk that two massive abandoned objects collide. This is more difficult, let's say, from the point of view economically, because who is going to pay for that? There's no customer because, or in many cases, no customers, because these upper stages have been put there by nations decades ago. That's one of the big issues. Who is going to pay for removing this, these relicts from 60 years of space activities? And again, the lessons learned from that is that we have to make sure that the operators which send up objects today, that we have enough incentives for them and penalties or whatever to make sure that they do a proper job in removing their objects, or going off for services to remove their objects if some of their assets become dead for whatever reasons.
Thank you very much. Very complimentary comment as well. Would Marie like to also add, since we talk about?
Yes, just a short note. I think we are really trying all together to find solutions, because there's one thing that we would like to avoid is catastrophic failures, cascading failures, and also perhaps drastic decisions, that would be taken, such as moratorium on launches or the idea of capping the number of satellites per constellation. I mean, there's been a range of ideas, that have been developed by some people because they see this as potentially really dramatic, with dramatic consequences, and we all want to avoid this. So yeah, I think it's important to put to draw the attention of people in policy to this question. It's not only a technical question. It's not only an industry question, and there is a bit. It's difficult for people in policy who have very little knowledge of this kind of issue to really understand the consequences. I think raising awareness to this question is one of our duty, and we also have to enhance corporate responsibility, social responsibility, matters of reputation of space actors. That will be key towards developing joint solutions.
Thank you very much. So I am now warned that we also still have some demo sessions left at the Tokyo venue. So despite this very interesting and fascinating topic that we have all learned so much about, thanks to our speakers, we must come to close this session. I would like to thank all the speakers from today. If I may start with session 1, Mr. Alexander Dumontlou, President of Space at Your Service at EPFL, Dr. Hendrik Kolvenbach from the Robotic Systems Lab at ETH Zurich, Professor Thomas Schildknecht from the University of Bern, Mr. Luc Pige from ClearSpace, Mr. Chris Blackerby from Astroscale, Professor Shinji Kimura from the Tokyo University of Science, and Ms. Marie-Valentine Florent, Executive Director from the International Risk Governance Center at EPFL. Thank you so much. Oh, excuse me. I also need to thank our sponsors and partners today. Most of all, EPFL, the Swiss Federal Institute of Technology in Lausanne, and the Leading House Asia of Switzerland. The State Secretariat of Education, Research and Innovation with its SwissNext network, and also Present Switzerland with its SwissTech campaign. Without these partners, this project would not have been possible. So thank you very much. And of course, most importantly, our audience, you at the venue and also online, thank you so much for joining us. And we look forward to seeing you at our next session tomorrow, if possible, at the venue or online. Thank you very much to everyone again.
Thank you.